Now in this case, as we worked it all the way through, we ended up with 0 over 35. Can we do 0 divided by 35? Is that allowed? Yes. 0 divided by a number is the one that we're allowed to do. It's the number divided by 0 that we're not allowed to do. So if the 0 is on top, we can do that. Because basically if you have nothing and you split it into 35 pieces, each piece is equally nothing. So for the x equals negative 10, we do get an answer of 0. And of course continue on and do the next one as well. Now in this case, as we plug in the negative 3, on the top I end up getting 0. On the bottom I end up getting 0. Well, can we do 0 divided by 0? Well, earlier we saw that yes, we can go ahead and do that if we have 0 on the top, but not when 0 is on the bottom. In this case, we have both of those. So which one wins? The one that wins here is the one that we cannot do. And so we actually cannot figure out what this value is. 0 over 0 is considered to be undefined, because anytime you have something divided by 0, it's considered to be undefined. So for this value, there is no value. And basically this idea right here, that some of our answers will be undefined, is the theme for today's work. Because as we continue working through rational expressions, we have to account for these values that give us undefined values. And those pieces that give us undefined values have a particular name, and of course we'll need to go into our notes accordingly. These are called restrictions. And so add this into your notes, and then we're going to see how it all plays out in some more examples utilizing what we just did as well. So as you take a look at the text here, the description about what a restriction is, you notice the restriction is the value of the variable, so something I can plug in for x basically, that would cause the denominator to equal 0, notice at any time. That's going to prove to be an important piece as we go through this. It's not just a matter of the answer, it's a matter of at any point could the denominator have equaled 0. And then restrictions are also called exclusions. Basically a restriction, it's called a restriction because it restricts the possible domain of values. All right, now let's go ahead and take a look at how we can actually use this and how it comes up in a regular problem. And we'll start by going back to that problem that we were looking at earlier. This is that same rational expression that we were evaluating earlier today. I want to start by simplifying this, and then we're going to say what the restrictions are. So let's practice the work we did yesterday. Please simplify this rational expression. And as you're doing that, hopefully you are remembering that the first step to simplifying is to factor. Because once we've factored it, then we can look for anything that might be multiplied into both the top and the bottom. And you see there's an x plus 3 that is being multiplied into both the top and the bottom. So those are going to cancel each other out. And so this whole thing simplifies down to be just x plus 10 over x plus 5. And that is directly on the heels of what we did yesterday. Nothing different so far. But today we are going to add one element, because you notice this one doesn't just say simplify, it also says to include any restrictions. So we now have to say, what can x not equal? Remember, a restriction is anything that would ever make the denominator equal 0. So like looking right here, what could I plug in for x that would make that equal 0? Negative 5. Because we're basically saying x plus 5 equals 0, subtract 5 from both sides. So x cannot equal negative 5. But again, it's anything that would ever make the denominator equal 0. If we look up a step, we had that x plus 3 in the denominator too. What could I plug into that parenthesis that would make that equal 0? Negative 3. So negative 3 is also a restriction. Now, why do we need this? Why do we care? Well, right now, if I plug negative 3 into this, well, that'd be negative 3 plus 10 over negative 3 plus 5, which would give me 7 halves, or 3.5. Okay, but didn't we test that earlier? Remember at the start of class, we evaluated 3 different values. We plugged in 3 different numbers into this same equation. The last one we did was negative 3. Remember what it gave us? That was the one that was undefined. So if I plug negative 3 into the original up here, it's undefined. If I plug it into the simplified version, it's 3.5. If this is truly a simplified equation, it should be equal to the original, but it's not there. That's why we have the restrictions here, because we're saying that yes, these two statements are exactly the same, except when x equals one of these values. So we're just pulling out the values that would cause us to have divided by 0 earlier. Everything else, we can cancel them out and not have to worry about it. But if it equaled 0, we would have a problem. And so that's the purpose of restriction, is to say that, yes, I can plug it in, and it's going to work for everything except for these few examples. And that'll come up also in a little bit of graphing detail, where that actually ends up being holes in graphs and some stuff like that. But basically, we're just adding one little detail to the fact that these are supposed to be equivalent. It's just they aren't always. So to continue practicing the idea of the restrictions and the work that we were doing yesterday, I'd like you please to simplify this rational expression and then tell me what are the restrictions on our answer. Yesterday we did a problem kind of like this, and we talked about how you had a couple choices, technically speaking, where you either could factor first or you could do the flip and multiply and then factor. That's technically true, but in this case you will make your life a whole lot easier if you do the factoring first and then flip your fraction, as you will see here in a moment. All right, so we work it all the way through. We factor first, then we multiply by the reciprocal here. Then we go ahead and combine it into a single fraction. Then I can look for anything that appears on both the top and the bottom that I can cancel out. And so anytime I have a pair of them on both the top and the bottom, cancel them. And you notice what we're left with here. We're left with just an x minus 2 over an x plus 3. That takes care of the simplifying part of the question. But of course, that's not the entire part. We also have the including restrictions part, which is our new part today. So for including the restrictions, remember, a restriction is anything that ever makes the denominator equal 0. Well, the first one that would leap out to us is, what can I plug into the answer that would make that equal 0? Well, what plus 3 equals 0? That'd be negative 3. So one restriction is negative 3, but it is by no means the only restriction here. Because, remember, it's anything that would ever make the denominator equal 0. Well, if I look up just one step from there, I see there were a whole bunch of other factors. And I need to now go through and set each of these factors also equal to 0. Now notice we already did the x plus 3, so that one's taken care of. But we got to do each of the other 3 as well. So I'm saying what minus 6 would equal 0. And then what minus 4 would equal 0, and then what minus 5 would equal 0. And so from that step, I now have 4 restrictions total listed. And yet this isn't actually all of them. The most complicated ones to find out all the restrictions are these division problems. Because with most of the problems, you can usually just look at like the step before you canceled stuff here to find your restrictions. But this is a division problem, and in doing division, we flipped one of the fractions upside down. So where this is the denominator in this step, this is the denominator in the step before. And because that was in the original denominator, I have to account for that in my restrictions. And so I'm now going to look up there and say, well, what minus 6 would equal 0? That'd be 6. I had already accounted for that one here, so I don't need to list it again. And then what minus 2 would equal 0? That'd be 2. I hadn't listed that, so I added into my list of restrictions. And remember why we have to do that. The whole idea here is that if I, for instance, tried plugging 2 into this original equation up here, I'd be trying to divide by some number divided by 0. And any number divided by 0 is undefined. It doesn't exist. You can't divide by undefined. And so we have to know that this will give us a different answer if I plug in 2 in the original versus my simplified form. And the same is true for all of these other restrictions. So that's why we have to include those, remember. Is because, in a way, you could say that the restrictions are the numbers that if I tried to plug them in, it would break it. Because it kind of breaks everything if we try to divide by 0. We cannot do it. So with this one, we know all of the underlying pieces, but we've never put them together quite in a problem that looks like this, so we might need a few little hints along the way. We can see that we are subtracting our two rational expressions. Well, anytime we're going to subtract fractions, we of course need a common denominator. Now you got a couple options about how you can do this. One is you can start right away by just going ahead and multiplying the first denominator by the second denominator to end up with one really big cubic denominator. But unfortunately, that cubic denominator is going to be a real pain to work with down the line. So while technically you can do that to get a common denominator, you're actually going to give yourself a lot more headaches down the line than if we take a slightly different tactic. Like so many of the other problems that we've been doing, like the one we just did, I'm actually going to make my first step to factor where I can. Now specifically, because I have to get a common denominator, I'm just going to focus on the denominator at the moment. I know that there is a little bit of factoring I could do in the numerator at the moment. I could actually factor a 6 out of that, but I'm not going to. I'm going to save that for the moment, and I'll explain why here in a moment. So instead, let's just focus on factoring that quadratic. Notice that factors into x minus 4 times x plus 2. Notice what that did for us. Both denominators now have x minus 4 in them. That means that I don't need to multiply them both by each other totally. The only thing I need to add in is this x plus 2. So I need to multiply that over into the other fraction, which means the fraction on the right there, that one can stay exactly the same. I don't need to touch it in order to have a common denominator. I only have to change the first fraction in this case, making our lives a little bit easier. So to make that the same, I'm going to multiply top and bottom of that fraction by x plus 2. Now again, those factored forms on the bottom are our friends. But you'll notice on the top I distributed. I'm actually handling the top and the bottom slightly differently, but that's just because I know down the line what's going to make my life a little bit easier. If you wanted to first write this as x plus 2 times x plus 5, you can. But please realize that in order to finish the problem, you'd eventually have to distribute in the numerator. The reason is because we're now going to go ahead and do the subtraction. Now, of course, when we do the subtraction, we need a common denominator because we know that denominator will stay the same. So we know our answer is going to be over x minus 4, x plus 2. I can leave that factored because you'll notice it's just going to stay the same. But on the top, in order to do that subtraction, I have to combine like terms. In order to combine like terms, the first thing we have to do is get rid of any parentheses that would have been there. So if you had left it in factored form in the numerator, you would now have to expand it out. All right, but now we're going to subtract here. Now pay very close attention when doing the subtraction. This is a common source of errors. My calculus students will make mistakes on this problem when they start rushing. And so learn the lesson now to be careful with it, because when we say that we are subtracting this, we are subtracting everything there. All right, let's see how that's going to play out then. The x squared, does it have any like terms over here? No. So that's going to stay in x squared. The 7x, does it have any like terms over here? Yes. So when I combine the 7x and the 12x, what are we going to get? It's not 19x, is it? Remember what I was saying about having to be careful with the subtraction? This is where that's going to happen. We got to do 7x minus 12x, which is actually going to be negative 5x. All right, next up is the 10. Does the 10 have any like terms over here? Yes. The 6 is a like term. So we're going to go ahead and combine those. When we do that, what do those combine to give us?
4.
And it's not 16. Because again, remember that we are subtracting everything there. So I am subtracting the 6, just like I subtracted the 12x. And so I'm actually going to be doing 10 minus 6, which is 4. And so this is what we get when we actually do the subtraction. X squared minus 5x plus 4 all over the whole x minus 4x plus 2. Now, the way this is currently written, we can't do anything else with it, but I think that we might be able to change the format a little bit to at least give us the possibilities. I left the bottom in factored form because it makes it really easy to reduce later. If the top were in factored form right now, I could know whether it was reducible. So, factor that top. Factor your numerator now so that we can see if this answer will reduce at all. And when you factor the numerator, you should get x minus 4 times x minus 1. Notice there is some simplifying we can do then, because in both the top and the bottom, I see an x minus 4. You notice the helpfulness of leaving the bottom in factored form now. I didn't have to refactor my denominator. Whereas if I had expanded it out up here, I'd have to factor it at this point in order to be able to know if it was reducible. So I tend to leave my denominators in factored form, and at least with adding and subtracting, you have to expand the numerators so you can combine them. And then later you have to factor it again. All right, now I'm going to go ahead and cancel out the x minus, which gives me x minus 1 over x plus 2. There we've completed the simplifying process. And this was basically new for us, doing a subtraction one. So a lot of little details, but there is one other detail that I want us to consider. The new part for today of restrictions. Take a moment before we talk about it together here. Think about what will those restrictions be. All right, so now for my restrictions. Remember, I'm looking for anything that ever makes the denominator equal 0. So basically, I'm now doing a little scavenger hunt. I'm looking to see what was ever going to make the denominator equal 0. Of course, in my final answer, I have this x plus 2, so I know I got to account for that. And the step above that, I also have an x minus 4, although I've already used the x plus 2. Okay, so I've found 2 so far. One's going to come from x plus 2, the other one's going to come from x minus 4. I'm going to keep looking up there, and I'm going to look to see if there was ever anything else in the denominator to worry about. Here, same 2. Same 2, same 2, same 2, same 2, same 2, and of course, this is the same as that, so I know that that's going to be the same there as well. So notice I only came up with 2 unique restrictions. So what plus 2 would equal 0? Negative 2. And what minus 4 would equal 0? 4. Those are our 2 restrictions. The order in which you write our 2 restrictions over here doesn't matter. If you wrote it as negative 2, comma 4, perfectly fine, because all it is just a list of numbers the order in which we list them does not change what they mean in